honor to be speaking here. As Jonathan said, this department's been very important to me in my life. It's arguably the reason that I'm British, and it's more seriously, it's been a big philosophical inspiration for me throughout my life, so it really is special to be here. Okay, so the background to this talk is that some of the things that I'm sort of interested in is thinking about how we can use formal tools in order to compare different theories in physics, in order to answer questions like, can we say whether one theory is sort of a better representation of the structure of the world, or can we really say that when two mathematical frameworks look kind of different, that actually they're equivalent to one another? And this kind of question has been important in several cases throughout history in physics. So to give you an example, at the birth of quantum mechanics, there are essentially sort of two emerging sort of forefront theories. There was what was called wave mechanics and what was called matrix mechanics due to Schrödinger and Heisenberg. And at the beginning, these were treated as two rival theories, and indeed these physicists sort of debated which one was right. But then von Neumann came along, as he did in lots of different fields, and what he showed was that really we can think of these two mechanics as actually equivalent to one another in a precise sense, and nowadays the kind of quantum mechanics we use is kind of a mix of the two. So today I'm going to be talking about another example whose origins come earlier in history, but has developments even later in history that are going to come up in this talk as well, and that's the case of Lagrangian and Hamiltonian mechanics. So what are these theories?
You might just need to click on the...
Just have to click on the right screen.
Okay, cool. Okay, so what are these theories? Well, essentially we can think of them as two kind of mathematical frameworks for describing theories in physics. So the history goes that Newton came up with his laws of mechanics that give one this law that relates the forces acting on some particles and its acceleration. Indeed, we learned probably in high school about this law F equals ma. And it was extremely successful, but it turned out that Newton's laws were quite difficult to apply to certain systems. And so new mathematical tools were developed to try and solve the dynamics for certain systems for which Newton's laws proved difficult. And these were called, the sort of two main ones were the Lagrangian methods due to the physicist Lagrange, and the Hamiltonian methods due to Hamilton, that essentially told us we didn't need to describe the system in terms of forces, we could do it in terms of something more like energy. And it turned out that these two kind of methods for thinking about Newton's theory were actually much more widely applicable to lots of other kinds of theories. So when it comes to thinking about field theories, relativistic theories, and even quantum theories, these two frameworks turn out to be useful as ways of thinking about formulating these theories. So what's the difference between them? Well, at least classically, the picture is that Lagrangian mechanics formulates a theory on what's called a state space that's called tangent space, where essentially the points of this state space consist of all of the possible positions and velocities of the objects involved. And the dynamics is given by what's called Euler-Lagrange's equations in terms of a Lagrangian function L. And we derive this equation of motion. You might have heard this principle of least action kind of thing. That's how one gets to this equations of motion. On the other hand, Hamiltonian mechanics formulates a theory on what's called cotangent space, where the points of cotangent space are all the possible positions and what's called canonical momentum of the particles, where canonical momentum is just a generalization of the notion of momentum that one has in Newton's theory. And the dynamics is given by what's called Hamilton's equations in terms of a Hamiltonian function h. So when we're asking about comparing these theories, we're asking, is there something importantly different about formulating a theory in terms of positions and velocities with this Lagrangian, and formulating them in terms of positions and momenta in terms of this Hamiltonian? And the kind of standard view is that the Lagrangian and Hamiltonian formulations of a theory, in as much as they both exist, are equivalent to each other. They're just two different ways of describing exactly the same physics. And indeed, this talk of them being formulations suggests precisely this, that they're just two different ways of getting at the same physics. And indeed, given a Lagrangian formulation of a theory, one can essentially construct the corresponding Hamiltonian theory via what's called the Legendre transformation that just takes one from a point on tangent space to a point of cotangent space by defining the momenta at some point as the derivative of the Lagrangian with respect to the velocities, and it defines a Hamiltonian function in terms of the Lagrangian one. And it turns out the other way around is also true. If we have a Hamiltonian formulation of a theory, then we can construct a Lagrangian theory via what's now called the fiber derivative of the Hamiltonian, but importantly, it does the same sort of thing. It takes one from a point of cotangent space to a point on tangent space by now defining the velocities in terms of the Hamiltonian, the momentum, and the Lagrangian in terms of the Hamiltonian stuff. And so what this seems to suggest is there's nothing sort of at stake in using the Lagrangian or the Hamiltonian way of doing things, because if we're in one framework, we can always translate over to the other framework and give the theory there, and vice versa. And so it seems like our sort of class of Lagrangian and Hamiltonian theories is the same. But it turns out that the picture isn't actually quite as simple as I just made it out to be. The reason is that it may not be that this transformation from the Lagrangian to the Hamiltonian side actually gives rise to a unique or well-defined Hamiltonian theory everywhere on cotangent space and the other way round. And in particular, we're going to be interested with a class of very physically important Lagrangian theories that are called gauge theories, and we'll say later on what they are. But importantly, this class of theories are such that the corresponding Hamiltonian theory is not well defined at all of the points on cotangent space. And what this means is that there's essentially no way to reconstruct the Lagrangian theory from the Hamiltonian one via this way of taking this fiber derivative of the Hamiltonian. And so this kind of picture where there's nothing at stake because we can always move back and forth doesn't seem to hold for this class of theories. So our question in this talk is going to be, is there a way to still maintain that Lagrangian and Hamiltonian formulations of these gauge theories are equivalent, despite the fact that we lose this ability to translate back and forth in the way that we suggested earlier? And indeed, so the standard physicists' thought is that these are equivalent, so part of this is sort of trying to make sense of whether that physicist kind of view can be reconstructed in formal terms. Okay, so the outline of the talk is going to be that I'm first going to go over in more detail what are these class of theories for which there is a natural way to move back and forth, and how can we sort of make precise the sense in which the corresponding theories are equivalent to one another. Then we'll turn to what these gauge theories are, say a bit more about what the Lagrangian Hamiltonian way of thinking about these theories is, and say why it's sort of philosophically interesting to think about their relationship. Then I'll turn to actually talking more about how we might interpret the relationship between them, and I'll sort of highlight some results that I have in this kind of vein, and in particular the way in which one might set up a kind of equivalence result that matches the one we have in the kind of usual easy case. And then we'll end with some sort of responses to this argument that look at some of the assumptions that we have to make in order to kind of get an equivalence between these theories. Okay. So to start us off with this sort of easy case, we'll just start with a sort of simple example of a Lagrangian that represents a simple harmonic oscillator. So a simple harmonic oscillator describes cases in physics like pendulums and springs where they have like a wave-like motion, and the Lagrangian can just be written as the kinetic energy of some particle represented by the position variable q minus some potential that here for the simple harmonic oscillators is dependent on the position squared. So we have this Lagrangian, and now when we take the Legendre transformation to define the Hamiltonian theory, we get that the momentum is just equal to the velocity in this particular example, and we can define the Hamiltonian from the Lagrangian via that way I defined earlier, and it's sort of well-defined and unique. And we can go the other way round. If we had this Hamiltonian as our starting point, then our fiber derivative of the Hamiltonian would now define the velocity in terms of the momentum, and now we could define the Lagrangian from the Hamiltonian. And one thing that one will see in this example is that the Lagrangian that we end up with is exactly the one that we started with. And it turns out that this is true whenever it's the case that this Legendre transformation and this fiber derivative of the Hamiltonian have the property of being what's called global diffeomorphisms. Essentially, it's just like the points of tangent space and the points of cotangent space are kind of bijectively related to each other. And this is called in the literature the hyperregular case. Why it's called hyperregular is not super important. It's sort of supposed to distinguish from the local diffeomorphism, but all that's important here is that in this sort of hyperregular case that we define it, we have this property that the Legendre transformation and the fiber derivative of the Hamiltonian are inverses of each other. And so like with our example, we can go over to the Hamiltonian side and do the translation on the way back, and we end up back where we started, and the other way around. And one can show that as a result, these hyperregular Lagrangian and Hamiltonian theories have exactly the same solutions to the equations of motion. So that is, if we think about the solutions to our Euler-Lagrange equations, they turn out to be unique for these theories, and we can map between the solutions in this bijective way. And in particular, if we sort of think about what these solutions look like on just our space of positions over time, then they correspond to exactly the same paths in our position over time space. And so when we're thinking about in what sense we have a kind of equivalence here, it seems like at least we can say that these theories are sort of uncontroversially, empirically equivalent. They make all of the same predictions because they have these same solutions. But often in the philosophy of science, we're sort of interested about whether we can capture a stronger notion of equivalence, particularly if we're worried about cases of underdetermination. That is, if we want to be realists about our theories, we don't want to be in a situation where we have two theories that say different things even though they make the same predictions. So what we want is something stronger than empirical equivalence, and indeed the fact that in these hyperregular theories, we have that we can translate back and forth such that they're inverses, so we might say they're sort of translationally equivalent, in scare quotes, suggests that maybe we can capture a stronger notion of equivalence, something like these theories have the same structure, or they can capture all of the same distinctions, despite the fact that one uses this tangent space and one uses this cotangent space. And indeed, one way of sort of formalizing the idea that two theories have the same structure is to draw from the recent literature on theoretical equivalence that suggests that one way to make this precise is to think about whether we can formulate these theories in mathematical terms as categories and then ask whether their associated categories are equivalent. And the reason why category theory is a sort of useful tool here is that it captures the idea that what theories are is they're really sort of structured set of models. They consist of some models, but also some isomorphisms or some equivalences between the models. And so when we're asking whether two theories are equivalent, we're asking whether they have the same models up to the equivalences. And indeed, these tools can be put to work in this example here. So define some categories of Lagrangian and Hamiltonian models to be such that the objects are just these hyperregular models or these hyperregular theories. And the arrows in this category, where the arrows just represent the isomorphisms, are just the transformations that preserve the structure of these spaces and preserve the Lagrangian and the Hamiltonian function, respectively. And then one can show, as Thomas Barrett does in a 2019 paper, that there exist functors, which are just maps between categories, that are equivalences in this precise sense, and preserve empirical content in the way I suggested earlier, where they map solutions back and forth. And even if one doesn't know much about category theory, it's pretty straightforward to see how this works. Essentially, what these functors do is they use the translations between the models that we defined earlier, and they use the fact that there's a way to take a structure-preserving map of tangent space to one of cotangent space. And then it says, okay, we're in the hyperregular context, and so one uses the fact that these maps are inverses to show that these functors must themselves be inverses on the objects and on the arrows, and that's sufficient to prove equivalence, precisely because it tells us that they not only agree about the class of models, but which of those models are distinct from each other. So now, taking a step back, this seems to suggest that we can capture the sense in which Lagrangian and Hamiltonian mechanics are equivalent to each other. Now, there are some ways one might try to respond to this and say, first of all, one kind of response would be, well, why should categorical equivalence capture our standard of theoretical equivalence? Maybe we want something stronger than that. Another thing to say would be, okay, categorical equivalence is fine, but the way you've defined these categories doesn't actually capture the structure of Lagrangian and Hamiltonian mechanics. So for example, the philosopher Jill North has argued that Hamiltonian mechanics actually has less structure than Lagrangian mechanics. And one way to make sense of that is what she's saying is that these categories don't actually represent correctly what the structure of these theories actually is. But those are not the worries we're going to be concerned with. We're going to be concerned with the fact that even if this captures equivalence between these hyperregular models, not all of our theories are hyperregular, and in particular, these gauge theories are such that their corresponding Lagrangian and Hamiltonian formulations are not hyperregular, because these maps are not these global diffeomorphisms. And so this doesn't provide the tools to say whether our Lagrangian and Hamiltonian gauge theories are even empirically equivalent to each other. And indeed, there's not sort of some natural way to drop this assumption of hyperregularity and still have this kind of categorical equivalence result in a natural way. Okay. So let's now turn to what these gauge theories are and how they differ from this kind of hyperregular context. So the starting point here is that while these hyperregular theories have these unique solutions to the equations of motion, in that given some sort of starting initial point, there's one possible evolution of it, these gauge theories are associated with there being non-uniqueness in the equations of motion. So given some initial point, there's lots of possible histories. And this arises from there being dependencies between the Euler-Lagrange equations. This was shown by Emmy Noether via a theorem called Emmy Noether's second theorem. Essentially, she showed how there's a relationship between there being dependencies between the Euler-Lagrange equations and these kind of symmetries between these non-unique solutions. And the idea is that although one has a kind of apparent indeterminism in the theory, the idea is that one can essentially recover unique evolution by treating the transformations between these non-unique solutions, which are called the gauge symmetries or the gauge transformations, as relating physically equivalent situations. And so the idea is that although we have a kind of apparent indeterminism, we should treat it as an artifact of the fact that our theories, our Lagrangian theories, has some variables in it whose evolution is underdetermined by the dynamics that we shouldn't think correspond to anything physical in the world. The only things that should be thought of as physically meaningful are the things whose evolution is deterministic, i.e. the things that are invariant under these symmetries. And one might ask, okay, why shouldn't we take this kind of indeterminism seriously? And it turns out the arguments are somewhat subtle here. There's a vast literature on it. But essentially the idea is that if we have some variables in our theory whose evolution is completely underdetermined by the dynamics, and all of our measuring instruments are subject to those same laws, then there's going to be no way in principle for us to ever sort of gain direct empirical access to the value of those variables. And so on sort of empiricist grounds, we should reject that they represent these sort of physically meaningful quantities. And the reason why we sort of pay attention to these theories is that it turns out that a lot of our best theories in physics are precisely of this form. So particularly in the context of field theories, theories like electromagnetism, lots of them, at least in some form, are these gauge theories, and they seem to be very important, which is why we sort of want to think more carefully about them. But just to give a sort of toy example that doesn't worry about field theories, just think about a Lagrangian represented in terms of two variables, q1, q2, and their associated velocities. So we have two particles in this universe, whose Lagrangian is just given by essentially the kinetic energy of the difference between q1 and q2. Then what it turns out is that when we do the Euler-Lagrange equations for this Lagrangian, for both the variable q1 and q2, they end up being the same equation. They end up being that the acceleration of this particle 1 minus the acceleration of the particle 2 is equal to 0. And so, because the equations of motion for this system are not independent from each other, they just give rise to exactly the same equation of motion, it turns out that this is a gauge theory. And indeed, the gauge symmetries are given by those transformations that add to q1 and to q2 some arbitrary function of time. And so the idea is that this represents a system where changing the absolute positions given by q1 and q2 while keeping the relative position the same doesn't correspond to a sort of physically meaningful different situation. The only thing that sort of matters here is what the relative position and the relative accelerations are. Okay. So now we've got to think, okay, what's sort of wrong about moving to the Hamiltonian framework now? Well, when we move to the Hamiltonian framework, what we do is we say, okay, let's take the Legendre transformation. When we do this, we can define the momentum corresponding to particle 1 and the momentum corresponding to particle 2. It's pretty straightforward to do it. We just take the derivative with respect to the velocities. But importantly, what one finds is that in this case, there's a relationship between these momentum. It has to be that P1 plus P2 is equal to 0. And what this means, because we have this restriction on these momentum variables, it turns out there's not a unique Hamiltonian function defined on all of cotangent space, because we don't have that these variables are independent of one another. And so it's not sort of clear initially how one would think about the Hamiltonian way of formulating these theories. But indeed, in the 1950s and 60s, some physicists basically worked out how to do it. It it was especially Paul Dirac, whose name you probably know, but also another influential physicist called Peter Bergman, and they sort of worked on this problem somewhat simultaneously but independently. And they developed this kind of way of thinking about gauge theories in a purely Hamiltonian way. And their sort of crucial observation was that gauge symmetry in this Hamiltonian way of thinking is associated with the presence of what are called constraints, which are just relationships like that P1 plus P2 equals 0 relationship, that have a certain kind of property called being first class. It's not sort of super crucial what that is, but sort of mathematically, it corresponds to these relationships whose Poisson bracket with all the constraints is 0. And importantly, what they showed is that while there are multiple possible Hamiltonian functions on this cotangent space, there is a unique Hamiltonian at the points of this space that satisfy all of these constraints. So there's in fact a well-defined way to give a Hamiltonian theory intrinsically in terms of just the points that satisfy these constraints that we have. Okay. So now our question in more precise terms is the Lagrangian formulation of gauge theories and the Hamiltonian formulation equivalent at those points where the Hamiltonian one is defined at those points that satisfy these constraints? And this is sort of a philosophically interesting question for several reasons that go past just problems about underdetermination. So for one of the reasons why physicists care about formulating gauge theories in this Lagrangian or Hamiltonian way is that it turns out that it's useful for thinking about how we can come up with quantum theories. So essentially, there's a sort of program in physics where, because quantum is our best sort of description of mechanics of particles, what we want to think about is all of our classical theories that we have, is there a way to essentially turn them into quantum theories? And it turns out that because there's a natural Lagrangian and Hamiltonian way of doing quantum mechanics, there's a way of think about those theories in the classical context and then turn them into the associated quantum theories. And because a lot of our best theories are gauge theories, this is a particularly useful thing. And in particular, if we're thinking about formulating a quantum theory of gravity, it turns out that general relativity is a gauge theory in this sense. And so, sort of thinking about formulating a quantum theory of gravity, we might think, how do we think about general relativity in this way and turn it into a quantum theory? And so, if it were the case that these gauge theories, even in the classical context, were not equivalent to each other, then one wouldn't even expect the corresponding quantized theories to be equivalent either. And that would be pretty significant for sort of analyzing these different methods of quantization. The second kind of philosophical interest is that there's a sort of deep philosophical puzzle that arises in the Hamiltonian way of doing gauge theories that's called the problem of time. And essentially this problem is that for theories that have a certain kind of symmetry that's called time reparameterization invariance, importantly includes theories like general relativity, what one finds is that the Hamiltonian function, the thing that gives the dynamics, is itself one of these constraints. And this has this weird conclusion that the things that don't vary under the gauge transformations are precisely the things that don't change over time. And so people have been deeply puzzled by this in giving us a sort of picture where we see things changing all the time, and yes, our physics says that those physically meaningful quantities don't change. And so thinking about the relationship between these gauge theories might help to pinpoint where one goes wrong, and in particular, in what sense is this a problem that only arises in the Hamiltonian way of doing things, or is there a similar kind of problem in the Lagrangian one as well? And finally, a sort of more niche application is that there's a debate that's going on within the Hamiltonian gauge theory literature about how we should actually correctly define what these gauge transformations actually correspond to. And the kind of standard view that's the Dirac view is that gauge transformations are generated by what's called an arbitrary combination of these first-class constraints. But there are some recent arguments in the philosophical literature, particularly by the philosopher Brian Pitts, that this Dirac view is just wrong. And why this is interesting is that one of his arguments is that only this alternative view that he provides is the one that matches the symmetries in the Lagrangian framework, and so it's the only view that preserves the equivalence between these formalisms. The Dirac view somehow breaks the equivalence between these two formalisms. And yet one doesn't find a clear account in this literature of what this equivalence actually amounts to. And so part of the task here is to try and resolve some of those issues by thinking more carefully about how we we can understand this relationship. Okay, so turning to what this relationship actually is, so the picture that we kind of have in the context of gauge theories is that if we imagine on the left-hand side that this space represents our tangent space. Now we draw it here as a three-dimensional space, which isn't quite accurate because it has to be even dimensional, but importantly, just imagine this is all our position velocity combinations. And then on the right-hand side here we have cotangent space, or the position momentum combinations. Now in the hyperregular case, all of the points over here map to all of the points over there quite nicely, and that's why we can go back the other way. But in the context of gauge theories, what we have is that the image of all of these points on the right-hand side is this surface here that I write as sigma p. It's called the primary constraint surface. It's all of those points on cotangent space that satisfy some of these constraints that are called primary constraints. And so the picture you should have in your head is that what's going on is that many points on the left-hand side are getting mapped to a single point on the right-hand side. And that's why this Lagrangian transformation is not invertible, because like with functions, if you have a many-to-one function, it's not injective, and so you can't sort of define as inverse. And indeed, the sort of fiber derivative of the Hamiltonian doesn't give one back this whole space. So our question is going to be, okay, how should we interpret this situation? How should we interpret the fact that many position velocity combinations correspond to a single position momentum combination in our Hamiltonian framework? And now there's a slight subtlety which I'm not going to talk about, which is that actually on the Hamiltonian side, these primary constraints are not actually all of the constraints one defines. And so actually on the Hamiltonian side, it can turn out that the solutions are actually only well defined on an even further subspace of this primary constraint surface. And so in the sort of some of these hard cases, some of the points over on the left-hand side don't map to any point on the subspace where the equations hold on the Hamiltonian side. And that's a problem that I talk about in the paper associated with this talk a lot, but we're sort of not going to worry about that problem here. We're just going to think we're in the context where we just have these one kinds of constraints that arise from this image. So all we're asking is, what should we think about this many-to-one relationship? And there are some views one could take. The first option would be to say, well, the naive picture is that Hamiltonian mechanics is under-describing the physical situation in the sense that there are more distinctions than can be captured by the Hamiltonian framework. Naively, our Lagrangian theory says that there are lots of different velocities this particle can have, where the Hamiltonian one says there's only one momentum that we can have. And naively, different velocities are different kinds of physical situations, and so we should think that the Lagrangian theory better represents these theories because it can make these distinctions the Hamiltonian theory cannot make. But we've got to remember, we're in this context of gauge theories where we have this kind of issue of non-uniqueness, and so we think that actually there are sort of lots of points, lots of variables that we don't think are actually physically meaningful, we shouldn't think of as representing different physical situations. And so if it's the case that these many points on the Lagrangian side that map to a single Hamiltonian point are gauge-related in this way, then it seems like maybe our option should be the opposite. Actually, we should think Lagrangian mechanics over-describes our physical situation in the sense that it makes distinctions that we don't actually think correspond to any physical distinctions. And so really, Hamiltonian mechanics better represents our gauge theories. Lagrangian mechanics has a kind of excess structure. It makes different distinctions that we actually don't think should be thought of as being distinctions at all. And then the final view one might take is to say, well, neither of these is right. Really, the differences that we're pointing to here don't matter. We can still maintain equivalence between these theories on the basis that these theories agree about what the content of these theories is that's invariant under all of our gauge symmetries, and that that's all that matters for equivalence. And indeed, this seems to be the sort of view that one sees that physicists kind of make. So what we're going to do is we're going to think about all of these options in turn and think about in what sense one can spell them out or not. Okay. So starting with this first view, so remember this first option was to say Lagrangian mechanics make some distinctions that are important that the Hamiltonian one doesn't. So what we need to ask is it the case that in the Lagrangian formalism that it does say that there's a physical difference between all of these points that map to a single point, or is it the case that they correspond to essentially points that are related by these symmetries? And one way to sort of think about answering this draws from a theorem that's shown by some physicists in the 1980s that's often sort of cited as showing equivalence in the context of gauge theories. And indeed, the title of this paper is something like Equivalence between Lagrangian and Hamiltonian theories for gauge systems, or something like that. So what do they show? Well, what they show is that the solutions to the equations of motion on tangent space map to the solutions on the primary constraint surface under this Legendre transformation, and the other way round under what they call the inverse Legendre transformation, which, remember, isn't sort of a well-defined function, but we can think of essentially what this thing does is it takes each point on the primary constraint surface to one of the points on the Lagrangian side that map to that point. So one of those arbitrary points on the left-hand side that map to the one on the right-hand side. So why does this help us? Well, coming back to this picture, essentially what this theorem is telling us is that if we have some solution to the equations of motion on our right-hand side, on our Hamiltonian side, and then we think about the sort of inverse image of that, where there are lots of solutions in its inverse image, differing by these different points that map to that single point on the right-hand side. Those solutions that differ just according to which point in the inverse the solution goes through are all related by a gauge symmetry. Why does it tell us this? Because essentially it tells us that if we take some Lagrangian function and think about its solutions, we get this non-uniqueness such that there's essentially a many-to-one relationship where all of the ones that differ just according to these points are all solutions. And so we have these many solutions to that same equation of motion to one over there. And so these are the ones related, some of the ones related by gauge symmetries. So if we're sort of thinking that gauge symmetries are supposed to relate physically equivalent situations, again, if we take this kind of standard view, then it seems like we can reject this first option. The distinctions that only the Lagrangian formulation makes shouldn't be thought to actually correspond to any kind of physical distinctions. They're all solutions that are related by a gauge symmetry. All of the ones that the Lagrangian theory says are different, that the Hamiltonian one says is the same. So this takes us to option 2, namely it seems like really what's going on then, if we think that there's this sort of over-description, then we should think that the Lagrangian formulation has a kind of excess structure compared to the Hamiltonian one. It says that there are these many points when really we only need one point to describe this physical situation. But now sort of, if we want to think about what it is for a theory to actually have excess structure, we need to think more carefully about what we mean by structure here. And in particular, what we want to think about is whether the points that we think are physically equivalent are actually distinct according to the structure of the theory. Or is it the case that they're just the kind of distinctions that we make when we sort of draw our tangent space down? So like with sort of, if we're doing things on a Euclidean plane, we often sort of write them down in terms of there being a 0 point, 1, 2, 3, 4, 5, 6 up, but we don't think that the actual sort of, there's a real significance to the 0 point that we draw because Euclidean space doesn't sort of pick out that 0 point. Here we're asking a similar thing. We sort of can write down these different points on the Lagrangian side, but are they actually distinct according to the structure of what these theories actually are? Or in other words, it seems like if we can think about the gauge symmetries as actually being isomorphisms of our theory, then there's a sense in which the theory captures exactly the distinctions that we want it to, even though there's a sense in which the sort of mathematical tools that we're using seem to over-describe our situation. And it turns out that actually there is a way to think about gauge symmetries as isomorphisms of the structure of Lagrangian theory. It turns out that it makes, to do this, we have to think about these theories in a kind of geometric way. And this takes us essentially a bit further far afield and relies on some parts of geometry that probably you aren't all familiar with. So just to give you the sort of highlights here for those of you that maybe are interested in this kind of area of geometry, essentially the picture is that our sort of primary constraint surface on the Hamiltonian side has the structure of what's called a pre-symplectic manifold. Again, the details here are not super important. Essentially, it's sort of a geometric way of thinking about these theories, where we think about the theories as formulated on a manifold like we have for our space-time theories, where it has a two-form on it, where a two-form measures something about this space. So in space-time theories, we have a metric that measures distances. This is kind of a coordinate-independent way of measuring something more like areas. And it turns out that on this primary constraint surface, this two form has the property of being degenerate, where degeneracy means there are essentially lots of quantities that get mapped to zero by this two form. And that's related to the fact that there is this kind of gauge nature of these theories. And it turns out we can think of tangent space as having a similar kind of structure. The way we can do it is we can define the two form on our Lagrangian side in terms of the two form on the Hamiltonian side that turns out to have exactly the same properties. Okay, so barring the sort of details here, the important thing is that what one can show is that once we think about these theories kind of geometrically in this way, one can show that the solutions on tangent space are equivalent to the solutions on the primary constraint surface up to the isomorphisms of the structure of these spaces that also preserve this Lagrangian and Hamiltonian function. So in other words, although there are these distinctions we can write down, the equivalence classes of solutions between these theories is exactly the same. And so it seems like there are no solutions that the Lagrangian theory distinguishes between that the Hamiltonian theory doesn't. And so when we're thinking about whether this theory has excess structure, it seems like the answer is no. Actually, when we're thinking about the distinctions that the structure of these theories make, they're exactly the same. Okay. So that takes us to our third option, which is think about whether all that matters is that the theories agree about this gauge invariant content, the stuff that doesn't vary under the gauge transformations. And we've made this more precise. We've said that this actually corresponds to the content that's invariant under the isomorphisms of that theory. And so if we think about those isomorphisms as capturing the physical content of this theory, it seems like this gauge invariant content really is what these theories say is the sort of structure of the world. And so at least it seems like we have an analog of the result in the hyperregular case that these theories are empirically equivalent. Instead of having that their solutions are in one-to-one correspondence, what we have is that their equivalence classes of solutions are in one-to-one correspondence. And so if that equivalence class captures what these theories say, it seems like they agree about the empirical content. But what we want to ask is, can we say something stronger? Can we actually use this to show a kind of categorical equivalence if we really want to get this kind of structural equivalence notion? And indeed, it sort of seems like we're getting there. What we have is that these theories seem to agree about things up to the isomorphisms. And remember that our tools of category theory were precisely meant to help us in capturing the sense in which theories agree about models up to isomorphism. But it turns out there's some sort of technical difficulties with proving categorical equivalence between our theories on tangent space and the primary constraint surface, precisely because of this issue about this map not being invertible, and in particular, going from a Hamiltonian theory to a Lagrangian one, it's not clear that there's a natural map to take one from this space that has fewer dimensions to one that has more. But it turns out there's some tools that we can use to actually help us here. And in particular, it turns out that it's much easier to sort of relate the structure of these theories if we formulate them directly in terms of their gauge invariant content. Or in other words, in terms of the structure of their equivalence classes. And one can do this in physics via a process that's very well known. It's called reduction, or it's sometimes called symplectic reduction. So what is this thing? Well, essentially the idea is that if we have some space, like our primary constraint surface, where we can think about all of those points related by some symmetry, which are just these sort of orange lines here. They're sometimes called these orbits. They're just all of those points that we think are symmetry related. Then it turns out one can define some other space such that the points of this other space just correspond to the equivalence class of points along this orbit, or there's a sort of many-to-one mapping from these points on this symmetry-related points to a single point on this other space. And it turns out one can do this in a kind of well-defined way. In particular, when we think about these theories geometrically, we can do this thing. And essentially, we can think of as what this reduced theory is giving us is just the description of the theory in terms of all of those things that don't vary under these gauge symmetries. And in particular, one can show that when we do this for the Lagrangian and the Hamiltonian theory, we can define a Lagrangian and a Hamiltonian on these reduced spaces. And one can show that there's a well-defined dynamics on this reduced space that's deterministic. So essentially, when we move to this sort of reduced space, what we're getting is essentially the content of this theory that tells us there's this deterministic evolution for all of these gauge invariant quantities, and I can give you a well-defined theory that gives you that. So now our question is, okay, what's the relationship between the reduced theories? Well, it turns out that one can show that the transformations between the reduced spaces, at least under nice cases, are themselves these global diffeomorphism maps such that they're inverses of each other. That is, one can in fact define the map that goes from the Hamiltonian one to the Lagrangian one, and it's just the inverse of the one that goes from the Lagrangian to the Hamiltonian. So in fact, our picture when we move to the reduced space is just like we have in the hyperregular case. When we define these theories in terms of the gauge invariant stuff, we can move back and forth in precisely the way we had in the hyperregular context. And so the steps towards sort of proving a categorical equivalence result are very natural once we're sort of thinking about the content of these theories as given by these reduced theories. We can just define these categories to be such that the objects are now these hyperregular reduced models, and the arrows are the transformations that preserve the structure of these reduced spaces and the reduced Lagrangian Hamiltonian. And then it's pretty straightforward, it just follows the hyperregular case to show that we can prove an equivalence between these categories. So as long as one thinks that these reduced spaces sort of capture the content of gauge theories, then it seems like we have that they're equivalent in just the way that the hyperregular case. That's the sense in which the sort of differences we had between the unreduced spaces don't seem to matter once we move to these reduced spaces. Okay. So let me just end with some responses that one might give to this kind of argument. So the sort of obvious response is to say there's something wrong with moving to the reduced theory. And in particular, there are good arguments in the philosophy of physics literature that the variables that vary under these gauge transformations can actually be very important, despite the fact they lead to this kind of non-uniqueness. So this is true in the context of the problem of time. Moving to the reduced space turns out to be extremely messy. But in other cases, so for example, in the context of electromagnetism, philosophers of physics talk about this phenomena called the Aharonov-Bohm effect, where what this phenomena essentially shows us is that when we move to the reduced space, we end up with a theory that violates the principle of locality. We end up with a theory that's non-local. And so if we think that that's a sort of important physical principle, it seems like there's something wrong about thinking about these theories as being captured by the reduced theories. And actually, I think this is a pretty reasonable worry. I'm worried about it myself. But one thing to say here is that what this talk has sort of highlighted is that this question is deeply connected with issues about how we think about what the structure of these theories actually is and how we're capturing their content in a kind of mathematical way. A second kind of response one could give would be to say that despite the fact that we've proved a kind of equivalence result, we should still think that one of these theories is more natural or more fundamental than the other one, or maybe there are some sort of non-epistemic reasons to prefer one theory over the other. So for example, we might say, okay, you've shown equivalence, but really we should think that the Lagrangian theory is more fundamental because the way we defined the Hamiltonian one was by thinking about the image of the Legendre transformation. Indeed, it seemed like what explained the presence of these constraints was precisely this kind of way we moved from the Lagrangian to the Hamiltonian framework. And equally, I think one could say something the other way round. One might say, no, actually, we should think the Hamiltonian formulation is more fundamental because there's a sense in which we sort of used it to think about which of those points from the Lagrangian side we should think of as being equivalent to one another. And the sort of strongest way one can sort of argue this, I think, is that if you were paying any attention when I was talking about the sort of geometry of the situation, the way we sort of think about this geometry of the Lagrangian theory is we take this 2 form on the Hamiltonian side and we pull it back to our Lagrangian side. And so we essentially sort of use the Hamiltonian structure to define our Lagrangian structure. And so it seems like we're not sort of thinking about the Lagrangian theory independently of the Hamiltonian one. So I think these two worries shouldn't tell us that there's something wrong with the showing this equivalence in the way that I did, but what they highlight is that these theories aren't really two completely independent theories. They're actually interrelated with each other in lots of ways, and actually thinking about the relationship between them actually helps to get at what the content of these theories actually is, or how we should treat their content, especially if we want to think of them as two formulations of a single thing. So at least what I hope this highlights is that sometimes sort of asking questions about the relationship between theories actually helps us to understand better those theories that we have at hand. Okay, that's everything. Thank you so much for listening.